Good afternoon. We are going to take notes on building functions from functions. We're also going to take some notes on how you determine the domain from these composites, which is something new for most of you. All right, Roman numeral 1, basic operations. Okay, topic number, we'll call it A, letter A. Understanding function notation. I find that most of the confusion when it comes to function form is a lack of understanding of how to read the function. So, for example, we have f of x equals x squared minus 1 and g of x equals x plus 1. All right, the first thing you need to understand is that the left side of a function expression, this part, is a description. And this description tells you the name of the equation, and it tells you what variables it's going to have. In this case, only x. Sometimes it has numbers, sometimes it has x and y. In this case, it's saying equation f with x's in it. So the right half of the expression is the actual math. It's what you calculate. So looking at the second example, g of x, the name of the equation, this is equation g, and it has x's in it. And then, of course, the math is on the right-hand side. Pretty simple when you break it down that way. When you evaluate a function, the notation, for example, would be something like g of 2 equals. In this case, it's an implied question. It tells you to go to equation called g, and then the 2 says replace x with 2, and then simplify. So g of 2 tells you what to do on the question. All right, well, let's calculate that. G of 2. Here's equation g. Replace x with 2. It will be 2 plus 1, which is 3. So g of 2 equals 3. Now, in the case of graphing, that's your x, so that's your y. G of 2 equals 3 is the same as the point 2 comma 3. That's Cartesian notation, that's function notation. Both of them can give a point. All right, so that's part A. Part B are your algebraic operations. Algebraic operations. Okay, we want to pay attention not just to the operation, but how you write it. So a sum is written f plus g of x, or it can be written f of x plus g of x. Both of those mean the same thing. And so we're going to use f and g, what we have at the top, and all you do is add them together. So x squared minus 1 plus x plus 1. And then you simplify, and since those add up to 0, you get x squared plus x. So 2 ways to write a sum. Okay, difference. Very similar. It can be f minus g of x, or it can be f of x minus g of x. They mean the same thing. So we take f of x first, so x squared minus 1 minus, and then we put in g of x, which is x plus 1. Notice the parentheses. So distribute the negative, you get negative x minus 1, and then simplify x squared minus x minus 2. That's what you get. Sum and difference. Okay, product. Product means multiply. And generally this is shown as f times g of x. I have not seen it f of x times g of x with a dot, but I don't suppose it's out of the question. So you take both functions and multiply them. X squared minus 1 times x plus 1. And in this case, we're just going to put dot, dot, dot. You end up with x cubed plus x squared minus x minus 1. Last one, quotient. Quotient is division. So it's usually written f over g of x. So we're going to take f of x on the top, so x squared minus 1, g of x on the bottom, x plus 1, and simplify. X squared minus 1 factors into x plus 1, x minus 1. So the x plus 1's cancel out, and our answer is x minus 1. All of these are pretty straightforward. When you're dealing with algebraic operations, we're going to go to C. The domain of the function from an algebraic operation, which is what the 4 things that we just did. Basically, there's 3 things you need to remember. You need to find any domain restrictions from function f, any domain restrictions from function g, and then after you've put them together, you want any new restrictions from the algebra. So if what you have created has restrictions that are new, you combine all of those. You put the restrictions on a number line, and the domain is what is left. Because restrictions are what x can't be, and a domain is what x can be. All right, so I'm going to turn the page. We're going to do a couple examples of this. Example 1. Let's say that f of x equals radical x and g of x equals radical x as well. We are going to find the product, f times g of x, which means, of course, multiply. Radical x times radical x equals some value x. Okay, so that's what it's equal to. Now we're going to work on the domain. So the domain for f of x is that x has to be non-negative, which means x has to be greater than or equal to 0. G of x has the same restriction, non-negative, x greater than or equal to 0. And are there any new restrictions? Well, x doesn't have any restrictions on it, so there are none from the new combination. So your domain is x is an element of the set containing 0 inclusive up to positive infinity. That would be the domain of the combination of the two. Pretty straightforward. Quotients are where things get a little crazier. So let's say that f of x is x minus 2 over x minus 3, and g of x is the square root of x. We're going to find f plus g and determine the domain. Okay, so first thing we're going to do is add f plus g of x and figure out what that function is. So x minus 2 over x minus 3 plus a radical x. Basically, you get a common denominator, dot, dot, dot. You end up with x minus 2 plus radical x times x minus 3 all over x minus 3. All right, let's do the domain. Okay, we're going to start with f of x. You can't divide by a 0, so any x that creates a 0 is not allowed. So if x is 3, it creates a problem. So x cannot be 3. Okay, now g of x. G of x, x can't be negative, so x has to be greater than or equal to 0. Now the new one, the only restrictions on the new one are the same. X greater than or equal to 0. And on the bottom, x can't be equal to 3. So it really didn't add any new restrictions to the domain. So this is one where you might want to graph the restrictions on a number line and get your domain from the graph. So we're going to draw a number line. And here is 0, 1, 2, 3. X can't be 3, so I'm going to put a circle around it to show it just can't be 3. And this says X has to be greater than or equal to 0. So X has to start at 0 and be greater than, but it has a hole at 3 because of this function. X can't be 3, so there's a gap on it. So that's your domain. So your domain is X is an element of, and it's going to have two pieces. It's going to go from 0 inclusive to 3 exclusive in union with, now on the other side of the 3 exclusive to positive infinity. And remember, when you have a hole, it goes on either side of the union symbol as excluded. So those are algebraic combinations, but there's actually a whole area of mathematics that's not algebraic. We're going to do compositions of functions. This is strictly something that we do in function notation, and it has some extra rules. Basically, composition defines the order of the functions applied to X. It tells you which one goes first and which one goes second. That order is always inside comes first, and then the outside comes second, and you could have something that comes third, fourth, or fifth. Okay, so notation. Let's say you've got f of g of x. And another way to write that is with a parentheses and a circle in between them. So in this notation, the function on the inside comes first, that's calculated, then the result is calculated second on the outside function. In this second notation, the g of x comes second, so it would be the first calculation, and then f would be the second calculation. So it definitely determines the order of things. All right, I'm going to flip the page. We're going to do example. All right, here's an example. Let's say that f of x is x squared and g of x is the square root of x plus 1. And we're going to calculate f of g of x. All right, so what this says is we are going to take function g, and we're going to replace every x in function x with that. So instead of x squared, we're going to have square root of x plus 1 squared, which ends up being x plus 1. Okay, let's do another one. Let's do f of g of 1. This says substitute a 1 into function g. Okay, so if I substitute a 1 in, that is g of 1 is the square root of 1.1, which is radical 2. So we did this part first. Now we take the result and we feed it into f. We replace every x in f with radical 2. So it's going to be radical 2 squared, which is a 2. When there's a number in the middle, you should have only numbers in your answer. When there's an x in the middle, you should have x's in your answer, unless something gets screwed up or it cancels out. Okay, so that's a basic example. Let's go through then the domains for compositions of functions. So we're going to call this B. That's A. So domain for compositions. Okay, so domains for compositions can be a bit interesting because number one, you take the restrictions of the inside function. And this is by itself, just the inside function. Then Number 2, you apply those restrictions to the outside function. And then number 3, you apply any new restrictions from the composition. So it's a little bit like a funnel. You start with all possible numbers, and then it funnels down to what's restricted for the first one, and then it funnels down to what's restricted for the second one, and then it gets even smaller when you add new restrictions to it. All right, let's do an example. Example 1. Let's say that f of x equals x squared, g of x equals the square root of x plus 1. We'll just use the same function. Okay, so we are going to do f of g of x. So g will be substituted into f, so that gives us the square root of x plus 1 squared, which is x plus 1. Okay, so we've done the composition. Now we're going to work on the domain. So for first thing you do is g of x. For g of x, the lowest value x could be as -1 because that will create a 0. From that, it can get bigger but not smaller. So for g of x, we start at -1 and then it can get bigger from there. Okay, now f of x. For f of x, by itself, there are no restrictions on this. So no new restrictions. F of x is just x squared. It's a parabola, so -infinity to +infinity are all okay. Okay, so that's number 1, we did g. Number 2, we did f. Number 3, we're going to do the composition, f of g of x. Looking at the composition, it's x plus 1. Well, that's just a line, and that would be no new restrictions because lines are -infinity to +infinity. So the domain for the composition, the only restriction was put on it by g of x. So the domain is x is an element of the set from -1 inclusive up to +infinity. Okay, example 2. Let's say that f of x is x squared plus 1, and g of x is 1 over x minus 1. We're going to find f of g of x. So g will go into f, so that gives me 1 over x minus 1 squared plus 1. And I'm going to do a little ... magic for the sake of time. We end up with x squared minus 2x plus 2 over x minus 1 squared. That's what we get. All right, I'm going to switch colors. We're going to do the domain. So for we do the inside one first. So g of x comes first. In g of x can't be 1 because it creates a 0. So we have a hole. For f of x, the one on the outside, x squared plus 1 is a parabola. So there's nothing new to restrict. It's all values. And then for the combination f of g of x, again, x can't be 1. So the only restrictions that we have are that x can't be 1. So your domain is everything but 1. So -infinity up to 1 in union with 1 up to +infinity. All right, let's do it backwards now. Same functions, but we're actually going to put the composite together backwards. It's going to be g of f of x, and that ends up being 1 over, and you substitute in, x squared plus 1 minus 1, which is 1 over x squared. Okay, so inside one first, f of x was a line, or parabola, excuse me, so -infinity to +infinity, no restrictions. G of x by itself was x can't be equal to 1, because then you'll have 1 minus 1 on the bottom. Now here is where things get interesting, because when I combine them, here's my new function. Well, if x is 0, it'll create a 0 in the bottom. So the new restriction is x can't be 0. All of those conditions together are the domain of the function. So if I throw these onto a number line, I have 0, I have 1. X can't be 0, so it gets a circle. Sorry, x can't be 1, so it gets a circle. X can't be 0, so it gets a circle. Other than that, everything else is free game. So down to negative infinity, the piece in the middle, and to the right, those are all domain. So let's write the domain. Your domain is, okay, we're going to start with the first piece, negative infinity up to 0, exclusive, in union with middle piece, 0 to 1 exclusive, in union with the right piece, which is 1 up to positive infinity. So on this one, you can tell that the composition of the two created a new problem, which is why x can't be 0 is because of the resulting composition. That's why we have to look at all three types. Okay. Roman numeral 3. Your book does this funny thing called decomposition, and there's more than one right answer to decomposition, but basically you're going to pull something apart. So for example, f of g of x, let's say that equals 3 over x plus 1. When you do a decomposition, you want to decide what could g of x have been, what could f of x have been. So try not to pick a plain x, that's not a true decomposition. But if we turn this into one function, the inside function, so x plus 1, then the outside function would have been 3 over x because g was substituted into f. Let's do one more and then we're done. We're going to do, let's say f of g of x is 4 times the square root of x minus 2. So you want to decompose it into its separate components, g of x and f of x. So let's make g of x the x minus 2. And then the outside function would be 4 square root of x because the x minus 2 was substituted in. That's decomposition, which is really pretty easy, and there are more than one answer. All right, that is it. Have a good afternoon.